In this online lecture, we're going to talk about the quick and dirty method to determine hybridization and what this helps us do and understand. So let me show you how this works. Let's say you take this molecule right here, ammonia, and let's say we want to understand this molecule at an orbital level. The first thing we would want to do then is to figure out the hybridization of the central nitrogen. And here's how the quick and dirty method works. The first thing you should understand is that single, double, triple bonds and a lone pair of electrons all have what's called one steric value. Each one is worth, let's say, one steric value or 1 point. So the quick and dirty method involves you first determining the steric value of that nitrogen. Notice he has a single bond right here that's worth one steric value. This is another bond right here that's worth another. This is also worth one steric value, and remember the lone pair is worth one steric value. Adding these up gives you a total of 4. And here's all that's left to do. If you happen to have a central atom that has a total steric number of 4, then he must be SP3 hybridized. If you get a total steric value of 3, then that means it's SP2 hybridized. And a total steric value of 2 means the atom is SP hybridized. So this central nitrogen is therefore SP3 hybridized. Now, in organic chemistry, remember we're only concerned with these 3 types of hybridization. That's why we're only concerned with the steric value of 2, 3, and 4. This is not the only way to determine hybridization, but it's a way that I'd like you to know just in case. So let's look at a sample problem here to make sure you got this. What is the hybridization of the carbon in formaldehyde? Let's first determine his steric value. He has one double bond here that's worth 1 point. He has a single bond here that's worth another, and this one right here, giving him a total steric value of 3. And a total steric value of 3 means that that carbon is SP2 hybridized. Notice this could be done mentally on an orgo exam and done very quickly. But why do we need to do this? Well, let me show you the advantage that you have here. Look at this sample problem. It says, what is the orbital description and bond angles for the following molecule? Notice in this question, they're asking us about the structural details of this molecule, which means we should have a good understanding of the type of bonding that's happening. And in order to understand the bonding, we should understand the hybridization. Now, what you're learning here is a method of analysis. So follow me as I analyze this molecule. The first thing I would do is look at this carbon right here and notice that he's bonded to these 3 hydrogens right here. So I could think in my head, that's what he kind of looks like here so far. We should also know that that carbon is bonded to this carbon right here to the right. So we'll place him right here in our structure. Now notice this carbon is connected somehow to this oxygen, so we can connect him this way to that oxygen, and we can put the H there as well. However, this wouldn't make sense. Remember, we know that carbon technically comes in 3 varieties here. Remember, he could be singly bonded like this carbon right here, or he could be doubly bonded right here, or he could be involved in a triple bond like this. Notice, going back to our example here, our carbon connected to our oxygen doesn't have any one of those 3 arrangements. So somehow we have to connect the oxygen and the hydrogen so that carbon matches one of those 3 situations. So what we can do instead is remove this, connect him to the oxygen like this here, and let's say we connect him to a hydrogen like this. This is still not one of our arrangements. So what we can do is simply double bond the carbon to the oxygen like this. And now we have an acceptable arrangement. This is a carbon that's doubly bonded to the right, and it has a sigma bond to the left and a sigma bond below. It's simply a doubly bonded carbon. Pretty soon, doing this is going to be very intuitive, which means you're just going to look at COH and know right away that this is the bonding arrangement for that carbon. So let's continue with this example. Speaking of Lewis dot structures, this oxygen would therefore have the 2 lone pair of electrons. Now let's look at the orbital description here. Look at the carbon on the left first. If we were to determine his steric value, we would get a total count of 4, which means this carbon has to be SP3 hybridized. That means his bonding looks more like this. And since he's SP3 hybridized, that means he has 109.5 degree bond angles. That causes one of his hydrogens to come out of plane here and another one to go behind plane here. And his orbital picture would look something like this. We would have the 4 sp3 hybridized orbitals, creating all 4 sigma bonds around this carbon. Now let's look at this carbon right here and understand his hybridization. Using the quick and dirty method, we get a total steric value of 3, which means that carbon is sp2 hybridized. And remember, we learned that all sp2 hybridized atoms have 120 degree bond angles, so a more real-life description of this bonding would be this structure right here. And because he's sp2 hybridized, this would be his particular orbital arrangement. Remember, sp2 hybridized atoms have the 3 sp2 hybridized orbitals and the unhybridized p orbital. So that explains the carbon on the right. And that also means this bond angle right here is also 120 degrees. Now remember, this original question was asking about the orbital description and the bond angles. Notice as we walk through this molecule and determine hybridizations, we're able to determine the value of all of the bond angles in this molecule. This is important for 2 reasons. 1, this could be a typical question on your organic chemistry test. And 2, we might need to do this as a first step to a bigger organic chemistry problem. This is an important skill. And notice what we're doing. We started with the condensed version of this structure, and through our analysis, we have a better understanding of the 3-dimensionality of this molecule. So the skill here is the ability to go from condensed structure to actual structure. Now, even though at this point we've answered all the questions here, let's do some additional analysis. For instance, look at this oxygen right here. We saw in a previous online lecture that oxygen could be hybridized. You could use the quick and dirty method on him. For instance, determining his steric value, you would get a total number of 3, which means this oxygen is sp2 hybridized. This helps us make sense of the fact that the carbon and the oxygen have a sigma and a pi bond between them. Notice, let's just focus on that bond right here. We determined that the oxygen is sp2 hybridized, so he has this orbital arrangement, and we previously determined that the carbon is also sp2 hybridized. The head-on overlap of their sp2 orbitals makes sense of the sigma bond between them, and the sideways overlapping of their p orbitals makes sense of the pi bond between them. And we could also make sense of the lone pair electrons on the oxygen. This lone pair right here would be placed in one of the sp2 hybridized orbitals, and this lone pair right here would have to be placed in the other sp2 hybridized orbital. So notice that analysis there. This means if the original question was, what orbital are the lone pair electrons in for the oxygen, we could answer that by using the quick and dirty method and understanding what each hybridized atom looks like. This is an extremely important skill in mastering organic chemistry.